AP Chemisters, this is Mrs. Vanderlei bringing you Chapter 11, Section 5, Blankwalle. This is about vaporization and later on vapor pressure. And before I really get into the notes, I want, just talk to you in general. What does it mean to vaporize? And you ought to know what that means. It goes from a liquid to a gas. And we have talked about before, like, why do you feel cold when you jump out of the shower? Because you still have little water droplets on you, which will absorb energy from you to become a vapor. So things become vapors without boiling, which we're going to address a little bit later on. And so if you have a beaker of water or a pot of water on the stove or something, just let it sit. Don't add any energy to it. Just let it sit at room temperature. But eventually what happens to that beaker of water, it disappears, doesn't it? So the entire beaker can eventually vaporize. If I put that beaker in, I spill it and now it's all over the floor, it'll probably vaporize a little bit quicker than it would in the beaker. So what's really going on here? Well, what I'd like to do is show you a quick video of a molecular version of what's happening when liquids, you think of water really, vaporizes. So let me try this. Let's see what happens. So what did you notice in that video? Did every molecule vaporize? Well, no. Okay, so next question. Which molecules did vaporize and which ones bounced into the gas phase? And if you notice, it wasn't the ones deep in the beaker, it was the ones at the surface of that liquid. So those are the ones that are vaporizing, are only the ones at the surface. So how did that vaporization occur? Well, that's when energy was added to break the intermolecular forces and produce a change in state from a liquid to a gas. So again, why do you feel cold when you jump out of the shower? It's because your body is giving it enough energy to break the intermolecular forces, and then it goes from a liquid to a gas. That's why you don't show up to school wet, right? So what can I do to change the rate of vaporization? Well, I can increase temperature for one thing. And let me show you a graph right here. Okay, here's a graph. Okay, and so this kind of goes back to what we did in Chapter 5 when we talked about things in the gas phase. So here we have kinetic energy, and this is the fraction of molecules. And notice that when it's a lower kinetic energy or lower temperature, if you will, aren't we all moving in a bigger pack? Remember my analogy? I said, let's all walk down to the UDF at the former 5-way. And this is before, class is over, so we're just meandering. Aren't we in a big group, and there's only a few folks going really fast and a few folks going really slow, but most of us are going about the same speed, right? We have about the same kinetic energy. But what happens when we realize, oh no, we're going to be late for the next class, we have to run back to school. So now our kinetic energy is increased, so we're at a higher temperature. What happens? We have more students running back at a higher rate, fewer folks are in the middle of the pack, and here's me in the rear end. Okay, so I'm coming up the rear. I'm not going very fast. But look what happens with molecules, with gas molecules. At a lower temperature, lower kinetic energy, all right, more molecules are at this average area. And when you increase the kinetic energy, you have now fewer in the middle, but what ends up happening, you have more at this outer extreme. So let's say this dotted line, it says here's the minimum kinetic energy needed to escape. So if I have a low temperature, some are still escaping, like right here. Okay, these are escaping. But if you increase the temperature, what happens? Now you have more molecules with enough energy to bounce out of the beaker. Okay, so that's kind of an important visual of what's happening here. So this is what I wrote. Okay, so the higher the temperature, the greater the average kinetic energy, but at any given time, one molecule have more energy than the average and can break free. So think about this. In the summertime, after it rains, how long do those puddles last? Well, not very long. But in the spring and in the fall, when it rains, those puddles will last a lot longer, won't they? So that's because the average kinetic energy for the spring and the fall is lower, so fewer molecules have enough energy to break loose and to go free. But those puddles eventually do disappear. Well, why is that? Well, it's kind of like what number 2 is all about. We know that increasing the surface area, what's going to happen? Well, which puddle is going to evaporate first? The one that is spilled over the floor, or the one that's in the beaker? Well, the one that's all over the floor, isn't it? Because it has a larger surface area. So how does that relate back to why it takes longer for lower temperature to evaporate than higher temperature? Because no matter what, only the surface molecules are going to be evaporating. So why does it take longer? Well, you still at low temperatures have molecules leaving that surface and are replaced by a different set of molecules, which will then, evaporate, which will be replaced by another set of surface molecules, which will then evaporate. So if you have lower temperatures, it takes longer to evaporate the whole puddle because you have to keep waiting for the surface molecules to leave, and then a new set comes in. On a warmer day, the surface molecules leave sooner, and then the next fresh batch can leave, and then the next fresh batch can leave. So, keep this in mind. It's only the molecules on the surface that are actually becoming a gas, and that's why, increasing the surface area then will also increase the rate of vaporization. So this results in more molecules are at the surface of the liquid. These molecules are held less tightly. You have fewer neighboring atoms to be attracted to. You only have the atoms below it to be attracted to and nothing above it. Vaporization will occur much more quickly. And then the other thing to think about is the intermolecular forces. If you have very strong intermolecular force, they'll be held more tightly. And it'll be less likely to vaporize. The weaker the IMFs, the less tightly the molecules are held, allowing more molecules to evaporate at a given temperature, increasing the rate of vaporization. So here, this is a direct correlation. Once you write that down, so as temperature goes up, the rate of vaporization goes up. That's a direct correlation. Did you write that down? What about increasing the surface area? That's also a direct correlation, isn't it? So the larger the surface area, the faster the rate of vaporization. But what about the strength of intermolecular force? The stronger the intermolecular force, the lower the rate of vaporization. They're held more tightly. You're going to have fewer gas molecules. So that's an indirect relationship. The greater the strength of the intermolecular forces, the lower the rate of vaporization. Okay, so make some kind of note to understand that for yourself. And so it says, why is vaporization endothermic reaction? Well, I've already kind of alluded to that at the beginning where I said the rate, or when you're jumping out of the shower, why do you feel cold? Because your body gives the gas molecules energy. Well, what is that energy actually used for? Well, it's used to break the intermolecular attractions. Hopefully that makes sense to you. Okay, so what's a heat of vaporization? Well, here you go. It's another delta H. Does that look familiar? So that's an enthalpy, isn't it? So it's the amount of heat, usually in kilojoules per mole, required to vaporize, well, here you go, 1 mole of a liquid to a gas. And the heat of vaporization of water is at its normal, say it again, at its normal boiling point is, are you ready? Check this out. Okay, 40.7 kilojoules per mole. Okay, so this is at its normal boiling point. And so this is what's happening in that transition when you go from a liquid to a gas. But what about condensing, going the opposite direction? What do you notice about the sign? So if you are condensing going from a high gas to a lower liquid, notice that that's an exothermic reaction. You have to lose energy to become a liquid. So notice that it's negative 40.7 kilojoules per mole. All right, so different substances have different heat of vaporization. Why? Due to the different intermolecular forces. So here's a list of those, all right, and you can see the different heat of vaporizations, okay? And notice that water has 40.7 kilojoules per mole at the boiling point. And rubbing alcohol has that OH group, if you remember. So it's also very high in hydrogen bonding. Acetone is dipole-dipole, as is diethyl ether. So you notice that if you have these two here, okay, water has a lot of hydrogen bonding. It has those two H's off of the one O. Rubbing alcohol only has one H off the O, although it has a greater molar mass, it still has a slightly less heat of vaporization. Acetone and diethyl ether are similar in their molar masses. They also are just dipole-dipole, and notice how these two are fairly similar as well, okay? So hopefully that kind of makes sense to you. Now notice there's also heat of vaporization at 25 degrees, so not at the boiling point, and you'll see what's going on here. So that's going from, again, liquid to gas. Okay, let's go to the next page. Well, as typical, if I give you a delta H, usually there's some math involved. So here we're going to calculate the mass of water that can be vaporized at its boiling point with 155 kilojoules of energy. So if you don't already have a calculator handy, why don't you get one? All right, well, hopefully you got your calculator handy. So we're going to calculate the mass of water in grams, all right, that can be vaporized at its boiling point with 155 kilojoules of energy. So it's like, all right, if my stove, maybe I have a propane gas stove, I'm out camping, and I can only have 155 kilojoules of energy released by the combustion of that propane. So how much water can I boil? Okay, that's really what's asking. So if a finite amount of energy, how much water will boil? So how am I going to do this? Well, how about factor labeling? That's always a good place to start. So I have 105 kilojoules of energy. What goes on the bottom? Kilojoules, very good. Why don't you flip over to the prior page, and how many kilojoules of energy does it take to vaporize 1 mole of gas, or excuse me, of water? Well, what did you find? Is it 40.7 kilojoules can vaporize 1 mole of water? Well, that's not what's being asked for. I want what? I want grams. All right, so let's go ahead and do this. 1 mole on the bottom, 18.02 grams, periodic table on the top. So what is my final answer going to be? Go ahead and calculate it. Okay, I got 68.6 grams, okay? So problem number 12 is very, very similar. Now we're reversing it. What if I have 2.58 kilograms of water? How much energy from my stovetop or from whatever will it take to vaporize that much water? Why don't you do that on your own and come back and see how you do? I hope we got this. I started off here. What I do immediately, I converted 2.58 kilograms into grams. Remember, to go from a big unit to a little unit, I need to multiply by 1,000 in this case. So now what? I need to put what on the bottom? Grams, periodic table. Thank you, I heard that. 18.02 grams of water in 1 mole. But wait a minute, I don't want moles. What is it that I want? I need kilojoules. All right, well, here we go. And 1 mole of water takes 40.7 kilojoules of energy to vaporize it. So I am needing 5,830 kilojoules of energy. All right, that's a lot of energy, okay? Well, it's a lot of water too, okay? So hopefully that makes sense to you. Let's try number 13. All right, so suppose you have 0.48 grams of water at 25 degrees condenses on the surface of a 55-gram block of aluminum that's initially 25. If the heat released during the condensation only goes towards heating the metal, what's the final temperature of the metal block? Specific heat capacity of aluminum. Oh my goodness, this goes back to chapter 6, doesn't it? So what did I write here? The Q of cond. Well, what does that mean? Condensation, all right, equals negative Q of the metal. So in other words, the heat released by condensing the water goes to the heat absorbed by the metal. Why don't you think about this and work it through yourself? Please actually try it and then come back when you're done. All right, well, hopefully you got something along these lines. So the Q of the condensation, I got negative 1.08 kilojoules. I converted that to joules. And then I went to MC delta T, the mass of the aluminum, and then specific heat, and then my final temperature minus 25. If you look at my math, I got 46.7 degrees is your final temperature. That seems rather ridiculous, I hope you realize, because what's the assumption that all the energy goes towards heating up the aluminum? How realistic is that? It's a good place to stop this video. So like I say, always don't wait to be great. We'll see you shortly. Bye-bye.